As I mentioned in our previous presentation, the term carbohydrate is a fancy way of saying sugar. There are two classes of carbohydrates: simple carbohydrates, which are also called monosaccharides, and complex carbohydrates. Simply defined, monosaccharides are molecules that consist of just one sugar, such as glucose, fructose, which are shown here. Complex carbohydrates are basically just polymers composed of two or more sugars bonded together. One example is sucrose, shown here. Sucrose, which is actually table sugar, is actually composed of one molecule of glucose and one molecule of fructose bonded together. Because sucrose is made of two simple sugars, or monosaccharides, it is called a disaccharide. And yes, as indicated in this picture, you can separate sucrose into glucose and fructose by heating it with acid. Cellulose, which is a complex carbohydrate that is the major structural component of most plant matter, is a large polymer of glucose molecules bonded together. Cellulose is made up of way more than two glucose molecules, however. In fact, typical cellulose molecule is made up of about 3,000 glucose molecules all bonded together in a chain. Interestingly, you can separate cellulose out into its individual glucose constituents also by reacting it with excess acid and probably a buttload of heat and time. Now, I should point out to you that huge polymers like cellulose are obviously not disaccharides because they're made up of way more than two individual sugars. To keep things simple then, we just call any carbohydrate polymer that's made up of 10 or more sugars a polysaccharide. Any complex carbohydrate that's got anywhere between 3 and 10 sugars we call an oligosaccharide. Now, simple sugars like glucose and fructose can be drawn in either an open chain fashion, which is what these structures here are, or in a cyclic fashion, which I'll explain later on. For now, let's just focus on this open chain way of drawing sugars. Just so you know, straight chain sugars that have aldehydes on one end, like glucose or ribose shown here, are called aldoses. And straight chain sugars with ketones in them, like fructose shown here, or acetoheptulose shown here, are called ketoses. We can categorize these sugars further by giving them names that correspond to the number of carbons in their chains. For example, an aldohexose is a 6-membered sugar that contains an aldehyde on one end. So glucose is indeed an aldohexose. An aldopentose is a 5-membered sugar that contains an aldehyde on one end. Ribose is an aldopentose. We also have ketohexoses, or a ketoheptose, for example. Fructose here is a ketohexose because it's got a ketone in it and it's got 6 carbons in its chain. And acetoheptulose is a ketoheptose. It's got 7 carbons in its chain and has a ketone inside it. I'll now introduce you to a special concept called D and L notation, which requires you to know the following background. The simplest aldose on Earth is glyceraldehyde, whose 2 enantiomers are shown here. And yes, I am showing them as Fischer projections instead of as the traditional wedge and dash structures we've become accustomed to in the past. The enantiomer on the left is called D-glyceraldehyde because it happens to be dextrorotatory. That is, it rotates plane polarized light clockwise. The enantiomer on the right is called L-glyceraldehyde because it happens to be levorotatory. That is, it rotates plane polarized light counterclockwise. Now, you might remember us talking about this light rotation concept called chirality back in Chapter 5 last semester. I want to reiterate now what I did back then. There is no direct correlation between something being R or S and it being dextrorotatory and levorotatory. Some R compounds happen to be dextrorotatory, others happen to be levorotatory. The only thing that we can say for sure is that if one enantiomer of a compound is dextrorotatory, regardless of whether or not it's S or R, then the other enantiomer will be levorotatory, and vice versa. Now, just so you know, D-glyceraldehyde happens to have an R configuration, and L-glyceraldehyde happens to have an S configuration. So as the field of carbohydrate chemistry developed, chemists began using this D versus L naming convention. And while we don't use this convention very frequently for other organic compounds, we use it a ton for carbohydrates. So how does the DL naming convention work? Well, here's how. When we draw a Fischer projection of a sugar, if the bottommost OH, which I've colored green in all of these examples here, is pointing to the right, then we say it's a D sugar. If the OH is pointing to the left, then it's considered an L sugar. That's pretty much it. It doesn't matter which direction the remaining OHs are pointing. All these other OHs up here, doesn't matter. The only thing that matters is if this bottommost OH here in green is pointing to the right, then it is a D sugar, and if it's pointing to the left, then it's an L sugar. And this all, of course, can only apply when we're drawing the open chain Fischer projection of the sugar. Now, I admit that this might seem a little confusing. If we look at D-ribose, which I've shown right here, for example, we might be tempted to think that, oh, it's a D sugar, so that means that it must rotate plane polarized light clockwise. In other words, it must be dextrorotatory. Oddly enough, that is not how the DL naming sugar works at all. Once again, here's how it does work. You look at the Fischer projection of the sugar, the open chain Fischer projection, and look at the bottommost OH, excluding the CH2OH. Bottommost OH, if it's pointing to the right, we say it's a D sugar, and if it's pointing to the left, we say it's an L sugar, regardless of whether or not that particular sugar happens to be dextro or levorotatory. Doesn't matter. So how did they come up with this crazy convention? Well, they just happened to notice that D-glyceraldehyde, which is dextrorotatory, has its OH pointing to the right when you draw it in this Fischer projection. And L-glyceraldehyde has its OH pointing to the left. They based the rest of the convention completely on that fact. Hence, every single sugar, when drawn in its open chain Fischer projection, follows that convention. The bottommost OH, if it's pointing to the right, is a D sugar, and if it's pointing to the left, it's an L sugar. And just in case you guys ever happen to be on a trivia show, you might be interested to know that almost all naturally occurring sugars happen to be D sugars. So, do you think you understand this concept? Let's take a look by throwing a few problems at you. First of all, I want you to categorize the following molecules as being D or L molecules. Let's take a look at this first one, threose. Once again, I need to look at the bottommost OH. I do not look at what's down here at the bottom, the CH3. I just look at the OH here that's pointing to the right, and I notice it is pointing to the right. Because it's pointing to the right, it is a D molecule. Here's a more complex molecule. Once again, I do not look at the CH2OH, I just look at the OH coming off of here. What is it? It's pointing to the right, therefore it's a D molecule. Here's a Fischer projection of a simpler molecule. I look down here, there's only one OH, and it's pointing to the right. So once again, it is a D molecule. Now let's see if we can apply this to molecules that look less like a sugar. Look at this compound, R-valine, shown here in its Fischer projection form. Is it a D amino acid or an L amino acid? How in the world do we decide that? Well, there's no OH, but we can still categorize amino acids by looking at the direction that the amino group is pointing in the Fischer projection. So I ignore this CH3, I look over here and look at the NH3. This positively charged ammonium, is it pointing to the right or the left? Well, it's pointing to the right. So what is it? It is a D amino acid. Now I'm going to bombard you with a pile of numerous reactions that simple sugars or monosaccharides undergo. Bombard, you might question? I suppose so. We could use that term anyway. But nearly every reaction that I'm going to show you here is one that you've already seen with simpler organic molecules before. So don't freak out. If anything, this should be somewhat of a review. So here goes. Aldoses, which you should remember, are just sugars that have aldehydes on one end when they're drawn in their open chain form. And ketoses, which are sugars that have ketones in them, can be reduced through treatment with sodium borohydride. So in this example right here, I've got D-glucose. If I treat that with sodium borohydride, which once again we can think of from our previous chapter's teachings as being like a source of H-. H- comes into this carbon, thrusts the electrons up onto the oxygen, and it gets protonated in water workup. This D-glucose can be reduced to this compound, which is called D-glucatol or D-sorbitol. Now, you might remember me foreshadowing earlier that all sugars exist in equilibrium between their open chain forms and their ringed forms. Thus, D-glucose, shown here in its open chain form, also exists in equilibrium with its ring closed form, shown here to the left. Now, before you proverbially crap your pants, just relax and don't worry about it for now. I promise I'll be talking about this in more detail later on, and I'll explain what is actually going on here. Another reaction we'll learn is this one. Aldoses can also be oxidized up to carboxylic acids, which are called aldonic acids. Thus, if I take this compound, D-glucose, which is an aldose because it has an aldehyde on the end, and I treat it with bromine and water, bromine can act as an oxidant and oxidize this aldehyde up to a carboxylic acid. Interestingly, when bromine and water is used, it only oxidizes up the aldehyde. However, if I use nitric acid and water as the oxidizing conditions, then it actually oxidizes up the aldehyde and this terminal primary alcohol. So let's compare these two. Once again, I go back. If I take an aldose like this and treat it with bromine and water, it only is powerful enough to oxidize up the aldehyde to the carboxylic acid, and it leaves this primary alcohol at the bottom alone. But if I take the same aldose and treat it with nitric acid and water, it's powerful enough of an oxidizing condition to oxidize up both the aldehyde and the primary alcohol to carboxylic acids. Now let's pretend that you have a cute little aldose like D-erythros shown here, and you want to somehow make it one carbon longer. How can you do that? Do you have to use magic? I'll tell you. We use this method called the Kiliani Fischer synthesis. Here's how it works. If I treat D-erythros with cyanide, then what happens, as we've talked about in the past, is the negatively charged carbon comes in to this carbonyl carbon and thrusts the electrons up onto the oxygen. That gets protonated in the acid workup to give me this intermediate right here. And do you see that? Cyanide comes in, electrons go up onto this oxygen, and it then becomes protonated, so it makes this OH right here. This compound, this nitrile, is now, you can see, one carbon longer in the chain than the original sugar that I started with. I can take this nitrile and treat it with hydrogen and palladium over barium sulfate and reduce it to this intermediate, which is called an imine. You might remember us talking about imines back in chapters 18 and 21. Once I get to this imine intermediate, I can then treat it with acid and water to hydrolyze off the nitrogen and convert it back into an aldehyde. I've effectively then taken my initial starting material, the sugar, and over 3 steps converted it into a sugar that is 1 carbon longer. Once again, what are the conditions? First step is cyanide followed by acid workup to give me this nitrile. Second step is I reduce with hydrogen and palladium barium sulfate to this imine. And the third step is hydrolyzed with acid and water to generate this aldehyde. Now that doesn't end the story, unfortunately. As you can well imagine, this cyanide nucleophile right here can and does attack this aldehyde with equal ease from both sides, three-dimensionally speaking. Thus, this first step, I can imagine the cyanide coming in from one side to push this OH three-dimensionally going to the right. But you could also imagine the cyanide coming in from the opposite side to generate this intermediate, which has the OH pointing three-dimensionally to the left. Now, believe it or not, these two intermediates are actually different. You should note that the only difference between these two compounds right here is the fact that they have opposite stereo configurations at this first carbon stereocenter only. In other words, all of the rest of the stereocenters, the one here and the one here, the one here and the one here, all have the exact same stereo configuration. It's only the stereo configuration at this position right here that's different between these two molecules. I hope you can see that. Now, if I have the cyanide come in and attack here, giving me this intermediate, I can then follow the exact same sequence. I reduce the nitrile to an imine by treating with hydrogen and palladium barium sulfate. And then I hydrolyze off the imine to convert to the aldehyde. You'll notice then that the final product that I end up getting by this sequence is different from the product that I get going in the sequence above. The only difference, once again, is the stereochemistry at this carbon stereocenter right here. In my Fischer projection here at the bottom, this molecule, diarabinose, has the OH pointing to the left three-dimensionally. The product of the sequence on the top has the OH at this stereocenter pointing to the right three-dimensionally. So, you might look at these two different stereoisomers and ask yourself the question, is there a name for these two different kinds of stereoisomers? Do we have a name for this? Well, as you may recall from Chapter 5, we do indeed have a name for it. These two compounds are obviously diastereomers of each other. But do we have an even more specialized name for them? Yes, we do. As it turns out, when we have two diastereomers that have the exact same stereochemical configuration at every single stereocenter except for one, then we call them epimers. Thus, if we compare these two stereoisomers, you can see that the stereochemical configuration at every single stereocenter is identical except for this one stereocenter. In D-ribose, the OH is going to the right, and diarabinose, OH is going to the left. So to reemphasize this point, when we have two diastereomers that have the exact same configuration at every single stereocenter except for one, we can call them epimers. So what happens if you're in the opposite scenario? That is, you want to shorten your aldose by one carbon. What can you do? Well, what you can do is submit your aldose to this sequence of reactions, which is called the Vole degradation. I'll go through the sequence of reactions here. Imagine I begin with D-glucose, and I'm in a situation where I want to remove one carbon from D-glucose and convert it into the sugar that would have one carbon less in the chain. Here's the sequence to which I would submit D-glucose. The first reaction is I treat it with this hydroxylamine and trace acid, and I generate this imine. It is an imine, but it's actually a special kind of imine where there's an OH coming off of the nitrogen. This is called an oxime, which we talked about in a previous chapter. If I take this oxime and I incubate it with this reagent, which is called acetic anhydride, and here's the full structure for an acetic anhydride, and then I heat this up, what occurs is a dehydration. It effectively removes this hydrogen and this OH and installs a bond here, so I have a carbon-nitrogen triple bond. In fact, I've just created a nitrile. You'll also notice that these conditions put acyl groups or acetyl groups on every single one of the OHs in this sugar. When I get to this stage, I then heat this intermediate up with base. The base removes all of the acyl groups and hydrolyzes it back down to the alcohols. And then I can take this intermediate and treat it with base and water again. Heat it up, and it effectively shortens this chain and gives me this aldose, diarabinose, which is 1 carbon shorter than the aldose that I began with. So let's take a look again at the sequence of reactions, the Vole degradation. I begin with this sugar, and I'm in a position where I want to have a sugar that has 1 carbon less. I take it, heat it up with trace acid and hydroxylamine, and I generate this oxime. I then take that oxime and treat it with acetic anhydride. It affects an elimination reaction, or a dehydration, which gives me this nitrile. The nitrile is then incubated with OH-. This hydroxide takes off every single one of these acyl groups to give me the free alcohols here. And then, at this stage, I heat it up with hydroxide again. It does a special reaction that I'll show you momentarily to shorten this chain. Those are the conditions by which I can shorten the chain of a sugar. Now, to avoid confusion, I want to draw out the mechanism for the last few steps of the Vole degradation. So once again, you might remember that this intermediate that we make, called an oxime, is treated with acetic anhydride. Here's acetic anhydride. What occurs mechanistically is the lone pairs on this oxygen come into that carbonyl carbon. Electrons go up to form a tetrahedral intermediate, which I'm not showing. And then the electrons collapse back down and kick off this leaving group. That gives me this intermediate. Now this acetate leaving group will then reach up, remove that proton, and thrust these electrons into the oxygen to neutralize the charge. That gives me this intermediate. Now this intermediate is special. What we've essentially done is we've converted this OH into an acetate. This acetate group is a very good leaving group. Now I haven't drawn it out, but you might remember from the previous slide that under these conditions what occurs is every single one of these OHs also gets an acetyl group put on it. I'm actually not drawing it that way because I'm trying to save myself steps, but I want you guys to remember that it does occur. At this stage, we take this intermediate and incubate it with hydroxide. The hydroxide comes in here, tears off this proton, thrusts these electrons down like a trapdoor, and kicks off this acetate leaving group. This is an elimination reaction. When it does this elimination, it generates this nitrile intermediate, and once again gives off this acetate leaving group. I also get water as a byproduct. Here's what happens next. This nitrile intermediate is incubated with more base. Now, I'm kind of doing a simplified reaction that may not be technically perfectly correct, but I still want you to see where all the reaction arrows go. This base can come here, strip this proton off, and take these electrons and dump them in here to form a double bond. When it does that, it kicks off cyanide as a leaving group and gives me this product, cyanide and water. So once again, you can see through this whole sequence, the effective result is that I've taken my initial sugar, my aldose, and removed 1 carbon in the chain and generated an aldose that is 1 carbon shorter. So here's where I'm electing to stop for now. Why? Because I'm tired, and maybe you are too. And I also have someone knocking my door right now. So let's take a quick break, after which I hope to see you for our final lecture on carbohydrates.